All right, how's it going, everybody? We are here. I'm recording this video on Friday, April 2nd. Today we're going to be covering section 8.2, the law of sines. This week in general, what we're going to be doing is we're going to be getting two formulas and seeing how to use them, the law of sines and the law of cosines. These two are going to represent sort of our techniques or algebraic relationships that are going to help us solve non-right triangles. And kind of weirdly, you should notice for a second that this is the first time this entire semester we've talked about a non-right triangle. We've only been talking about right triangles for the first 10 weeks of this course, and we're finally just now suggesting that maybe we want to be able to deal with some non-right triangles as well. And what we're going to end up finding is one, we can't directly use our trig functions anymore to talk about our triangle side lengths because our trig functions are defined by sides like adjacent, opposite, and hypotenuse. And we don't have a hypotenuse anymore. By definition, the hypotenuse is the side that is opposite of the 90-degree angle. And if we're talking about non-right triangles, we don't have a 90-degree angle. So we don't have a hypotenuse anymore, which means our definitions of sine and cosine being things like opposite and adjacent, we're going to kind of lose that sense. So we can't directly use our trig functions like we did in 8.1 to solve triangles. However, what we know is that since all of our trig functions are defined based on right triangles, even though the triangles we're going to be solving today are not right triangles, we're going to want to create some right triangles within them so that we can get access to our trig functions once again. So just some quick vocabulary since we now have lots of different kinds of formulas out here. These are a bunch of words where I'm assuming mostly everybody has mostly at least seen most of these words in their lives, but I know that not everybody has exactly the right definitions for these probably in their head. So take a quick moment here, check out this list of just some words that you're going to see thrown around by me, by the textbook, by my open math, stuff like that. In general, all triangles are either right or oblique. Oblique just means not a right triangle. It doesn't have a 90-degree angle. If all of the angles within the triangle are less than 90 degrees, then we say it is acute. If one of the angles is bigger than 90 degrees, then it is obtuse. And you should notice that since the total amount of angle inside of any triangle is 180 degrees, if one angle is bigger than 90 degrees, then the other two combined are both smaller, even combined are less than 90 degrees. So it's not possible for a triangle to have two angles bigger than 90 degrees because then it would add up to more than 180, right? So in general, we've got our right triangles versus our oblique triangles. That might be my oblique right there. For acute triangles, we might have something that looks like this guy right there. For our obtuse, we might have something that looks more like this triangle right here. Clearly a larger than 90-degree angle sitting up top right there. If a triangle has no equal side lengths, then it is scalene. I think that's maybe a scalene triangle right there. If it has two equal side lengths and therefore two equal angles, then it is isosceles. And so we get this being like x, and these two angles being the same. I think typically in geometry, whether we know the angles or not, if we indicate them with one bow, it's equal to the other one bow, and then this two indicates that it's different than the other. Finally, if all three side lengths are the same, we call this an equilateral triangle when all three sides are the same. And if all three sides are the same, it must be that all three angles are also the same right there. So just a bunch of triangle words that are out there. The big ones that you're going to see, I think, mostly are oblique. Scaly never really comes. I've never seen that, I don't know, directly referenced in our book or homework, but I don't know. That's one of the words that goes in this family of words out here. So just kind of be aware. This is our general triangle vocabulary here. So in the last section in 8.1, we categorized our triangles by how many side lengths we knew. We're going to do that again today for our non-right triangles. And really what we're doing right now is we're sort of setting the stage for both videos this week. We're going to talk about when are we going to use law of sines, when are we going to use law of cosines right now. Then today we'll derive the law of sines and use that. So there are three sets of cases for any general triangle. In general, we're going to need to know at least 3 out of 4 pieces of information for any general triangle here. So let me draw a general triangle right here. And so in this triangle here, as we kind of talked about last class, we typically use capital letters or Greek letters to indicate angles and we use the lowercase letters on the opposite side to indicate side lengths. One of the major difficulties with this is that C and C are going to look the same quite a bit. I'm going to do my best to make sure that the capital one looks capital and the lowercase looks very lowercase. But again, remember that the really important thing here is that these are tied to each other. C is across from C, B is across from B, A is across from A. This is a very helpful style of notation that helps us not have to draw a picture to communicate a triangle to somebody here. We can just use like letterings right here to make our relationships be consistent. So the other statement here that I'm going to say is that there are always 6 pieces of information about any triangle. There's all 6 pieces of information, 3 angles, 3 sides. And the deal is going to be is that we're always going to need to know at least 3 pieces of information about any triangle to be able to solve that triangle. So for a right triangle, I can give you 2 pieces of information, but you really have a third because you know that it's a right angle. So in general here, we always need to know at least 3 of these 6 numbers. And then if we do, we'll be able to solve that triangle right here as long as, well, let's go right into this, as long as we know at least 1 side length, right? And so basically, if we know 0 side lengths, just knowing all 3 angles will help us determine our ratios of side lengths. Let me say that. Just knowing all 3 angles can tell us the ratios of side lengths. But the triangle could be of any size. So that's saying to me, we actually can't solve these triangles if we only know angles. We need to know at least 1 piece of side length information to get information about what the other 2 side lengths are going to be based on the other angle information that we know. Our second grouping of cases here is going to be the triangle situation where we either know 1 side and 2 angles, so there's our 3 pieces of information, or we know 2 sides and 1 angle. These are going to be the cases that we can solve using law of sines, what we're going to get today. Finally, if we know all 3 sides but no angles, a little bit different set of information here. These we are also going to be able to solve, but we won't be able to solve this using today's formula. We'll be able to get this one using tomorrow's formula, the law of cosines. So in our next video, we'll cover how to do case 3. So basically the point is, of the 3 sets of information that you could know, you know no side lengths, you can't solve it. If you know 1 or 2 side lengths, you can solve using the law of sines. If you know all 3 side lengths and no angles, we can solve using the law of cosines. This is sort of breaking down all possible general triangles that might be out there. Can we solve them? Can we not solve them? If we can, what technique are we going to use? So this is basically kind of our strategy for this week so far. So basically the deal is going to be that today and tomorrow, we need to sort of start by determining what is this formula? How do we construct some formula of relationships out of a non-right triangle? And we'll do that right now, and we'll do that to start our next video as well. And then we'll use that in practice there. So let's talk real quick about how this algebra is going to pan out here as well. Today we're covering case 2. Next video we're covering case 3. So the deal here is going to be that we're going to either know 1 side and 2 angles or 2 sides and 1 angle. So what that sort of says to me is that the law of sines must involve 2 sides and 2 angles if we're going to be able to take in either of these sets of information. And therefore what it's going to solve for is the 4th unknown piece. So if we know 1 side and 2 angles, we can use the law of cosines to solve for a second side. Alternatively, if we know 2 sides and 1 angle, we can use the law of sines to solve for a second angle right here, and then we can proceed on with solving the rest of the triangle, right? So law of sines, I'm going to say contains 2 sides, 2 angles. Oh, falling off the side of my screen there. And the law of cosines, on the other hand, it looks like it's going to take in all 3 pieces of information about side length, and therefore the only thing to solve for would be an angle. And so hopefully you can sort of logically deduce that the law of cosines should instead be containing three sides that we know and the one angle we'll be able to solve for. Um, so that's just sort of our layout of what these formulas are going to look like here today. So as I'm kind of saying in the paragraph down here, our hope today is to be able to create a formula that involves two sides and two angles so that we'll always know three out of the four pieces of information, allowing us to solve for the fourth. In the next section, 8.3, we'll want to create a formula involving three sides and one angle, so that we'll be able to solve for an unknown angle. And then if we can solve for a second unknown angle, then the fact that all three angles add to 180 will get us the third one, and we'll be done solving right there. So let's go ahead and derive this formula that we're going to call the law of sines. It's going to be called the law of sines because it's going to use a sine function. Guess what? Tomorrow the law of cosine is going to involve the use of a cosine function. Not really going to, the trig here won't necessarily blow your mind, I don't think. But using these formulas takes a little bit more than just the basics of like opposite over adjacent, right? We're going to need a little bit more work than that. So the other thing about this is that I'm going to do the proof using an acute triangle. The book's proof involves an obtuse triangle, an obtuse triangle. And so this is basically just my way of sort of saying like, yeah, this works in general for all of them. In a technical sense, if you wanted to be super duper sure that this formula was always valid, you'd want to check it, create it once with an acute, once with an obtuse. I'm not going to just do the process twice here. You can partially take my word for it and partially look in the book. And this formula is not going to be too crazy to construct here anyway. So the key here is that we only know how to use our trig functions when they're associated with right triangles, because they all are defined on these ratios of like opposite over adjacent, opposite over hypotenuse. And we lose those definitions when we no longer have a right angle from which to sort of like anchor our relationships in the triangle. So what are we going to do? Since we don't have right triangles, we're going to make right triangles. This is just a typical mathematician thing to do. If you need something, you just introduce it into the situation in which you need it. So what we want to do right now is we want to consider a general triangle, and then we're going to draw one extra line on the general triangle to make a triangle that does have right angles in it so that we can then make some new relationships. All right? So what we're going to do is we're going to consider a general triangle here. So I'm going to draw a general triangle here, just some old triangle. I'm going to label some angles of A, B, and C. And I'm just trying to keep my labelings consistent with my notes here, A, B, and C. And so the point is here, none of these angles are considered to be 90 degrees. But what I'm now going to do is I'm going to drop down a vertical line from the angle B right there. And what this is going to do is it's going to make that be a right angle and that be a right angle. So the good news is by dropping down that extra vertical line right there, what I've done is I've sort of created two right triangles, which means that I can talk about trig relationships with them. But the bad thing that I've done is that now it seems like relative to this right triangle here and this right triangle here, it seems like this dashed line's length is now something I'll need to actually know to be able to discuss. So I've actually introduced a seventh piece of information here other than the three sides and three angles. There's now what we might refer to as the height of this triangle right here. So that's sort of our introduced piece, is that H right there. So what I don't want to have to do is think about H's actual information, because H isn't relevant to me for solving the triangle. However, you should notice that H is a connecting piece of information between the two right triangles that we formed. So we don't want a formula that includes H. We want to solve for A, B, C, A, B, C. However, H is the connecting piece of information between the two right triangles that we created. So what I'm going to go ahead and do is I know that H is going to be sort of my piece of information that's going to help me relate the left triangle to the right triangle. And based on my like cheating hint that I know that we're looking to construct the law of sines, what I'm going to do is I'm going to make two statements about the two triangles that we're looking at right here. Right. So the two triangles that I see here are the A. I know this is C, and I know this is H. Notice that we don't know this upper angle because B has been chopped and I don't know how much it's been chopped by. I don't know this lower side because B has been chopped and I don't know where the chopping happened at. So this is all I know out of that triangle. The other triangle, I have a very similar situation here where I know this is angle C. I know this is side length A. This is part of B that's been chopped and I don't know by how much. I do know that's the height H. I do know this is the other part of B and it's been chopped, but again, I don't know by how much. So what I'm going to do is I'm going to make two trig statements that I can about these right triangles using only the pieces that I know. You should notice that angle A, relative to angle A, the only angle I know in this triangle, it should be relative to that, I know the opposite is H and that the uh, hypotenuse right here is C. And so opposite and hypotenuse tells me this should be sine information that I want to talk about. So I'm going to say that the sine of A is going to be opposite H over hypotenuse C. Similarly over here, I can say that H and A are opposite and hypotenuse relative to angle C. And therefore, I'm going to say that the sine of C is H over A. And notice that now what this is going to do is it's going to help me relate these two equations to one another. Notice that what I know is angle A and side length A, angle C and side length C, and H can be a connecting piece of information between them. So here I'm going to multiply C over to the other side. C times sine of A equals H. Over here, same thing. A times sine of C equals H. And therefore, it seems like this quantity must be equal to this quantity right here. I'm going to go ahead and say plus right here. And therefore, it should be that C sine A equals A sine C. And what's typical here in this case is to do a little bit of division to get the A terms together and the C terms together. So I'm going to divide this A to the left, and I'm going to divide this C over to the right. And we're going to get a statement that looks like sine of A over A equals the sine of C over C. And this is what we refer to as the law of sines right here. This is exactly what we wanted, which is a formula that has two angles and two sides. And therefore, as long as we know any three of the four pieces of information in this formula, we can always solve for the fourth. Another thing to notice right here is that it's also definitely the case that we could set up the statement sine of B over B. This together was really just an arbitrary selection of letterings right there. I could have just picked different letter names to include B instead of A and C right there. There's nothing special about this being A and C. It's really that for any opposite angle side relationship, A and A, B and B, C and C, we can always set up any two sides of that equal sign that we want as long as our information matches top and bottom right there. So this is our law of sines. This is what we're going to use to help us solve non-right triangles here. Notice it does use trig functions, but they're no longer directly representing opposites and adjacents and hypotenuses of the overall triangle, but instead sort of one that we've created by dropping that vertical line and creating two right triangles within the overall triangle. So the bottom line with this is that this is going to be sort of easy, except for one special case that's actually going to have a couple different possibilities that can happen with it, and we need to be a little bit careful. That case will be easily identifiable for you so that you'll be able to say, ooh, this is one of those ones where I've got to watch out, versus other ones where we don't necessarily have to watch out. And by the way, I'm seeing here, I've got some notation that I've got right here. I want to scroll up for a minute and sort of make some statements that look like this up in our categorizations up there. I realized I forgot to mention that. So in general, the cases here are classified according to angles. If I think of angle as an A and I think of a side as an S, then we would refer to this as angle, 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 right? This is knowing no side lengths, but knowing all three angles. This would be an angle, angle, angle triangle, where the three, that's just listing what three pieces of information that we know. Here, if we know one side and two angles, the two things that could happen are, it could either be the case that the side that we know is between two angles that we know. So that would be like knowing A and B as angles and side length C. Or it could be the case that we could know two angles and then a side. So like knowing angle A, angle B, and then side length A, to where the side length is not in between the two angles, as indicated by the ordering of the letters right here. So these are our two cases here for two angles, one side. The other cases that we have over here would then be sort of the opposites of these, right? We could have a side angle side, where we know something like side length C, angle B, and side length A. And then our final case is where we know the angle, but it's not between the two sides, and it is going to very appropriately get labeled as ASS, because this is going to be the case that's going to bother us the most. So there's your little hint as to how you're always going to remember which is the case that's going to be the most obnoxious to deal with. We're going to be able to deal with all four of these cases here today. This right here is the one where we've got to watch out for a little funkiness that might end up happening right there. So there's your little notification as to how you can tell that this is coming. Finally, just to kind of wrap this up, this guy down here would be referred to as a side-side-side triangle, where the three information pieces that we have are the three sides but no angles, right? So it's typical to classify triangle information based on the number of sides, the number of angles, and the order in which they appear on the triangle in which we know them. Is the piece of information of the side between two no angle or between two known angles, or is it two known angles then the side as you kind of like take a trip around the triangle there? So these are our four cases here for today. We're going to watch out for the potty mouth one right there. Okay, so our first cases then are the two that are not that case, and then you should notice we're going to be covering several special cases of this one right here to make sure that we see all of the behavior that ASS will provide for us here. So here's our 5 examples here for the day are these guys. So let's go ahead and use the law of sines. These two are going to be the relatively easy ones, and some of these will be easy too, but we're going to see if there's, again, like I said, we got to just be more careful, be more mindful when we see these scenarios crop up. So another thing that's really important here before I do this example is this. You're in general not going to be like told this kind of stuff. I'm not going to say to you, my open math is not going to say to you, hey, solve this AAS triangle, non-right triangle right here. Like that's not going to be told to you. In general, it's just going to say solve the triangle. And I think that the smart first thing that you should do for yourself is draw the triangle and decide for yourself what case that we're in right here. So if I were to do this right here, and I generally try and just always draw this same triangle right here. As soon as I say that, I start lettering. My alphabet apparently starts at B today. Okay, so just trying to draw this same triangle up here, always, always, always. ABC, and then we get an ABC. So I'm going clockwise around this thing, starting in the lower left. A, B, C, and therefore A is opposite A, B is opposite B, lowercase c is opposite capital C. And so in our case here, we're going to get, what do we know? We know that angle A is 40. I'll throw this in here. I know that angle B is going to be 60, so I'll put this here. I know that side length A is 4. So this is how you can see that we have angle, angle, side. If you're taking a trip around this thing in one direction or the other, it doesn't even matter. Angle, angle, side, or side, angle, angle, if you're going in the other direction would be an appropriate way to say this. The reason this is not angle, side, angle is because we don't know an angle, a side, and then the very next angle. This is unknown right there, right? So you could call this AAS or SAA would be two appropriate ways to state what type of triangle this is right here. So as it goes, we know what our deal is here. We're looking to solve for all 6 pieces of information. We currently only have 3 pieces of information. So we want to use the law of sines to help us solve for some values here. So what I'm seeing here is that the law of sines says to me, what I really want to know is one complete pair of information, two of the matching letters, right? B and B, or A and A, or C and C. It looks like in this case, I know A and A. So that says to me, I want to set up a piece of information, one side of my equal sign being the sign of A over A. The other piece of information that I have is capital B. And so it seems to me like I'm going to be using this right chunk over here. And it looks like the piece of information that we'll be able to find first is lowercase b, because it's the one that's the missing partner right here. Right? So I'm going to say from given info, can solve for B first. So I'm going to go ahead and set up my sine of A over A equals sine of B over B. It looks like relative to the information that I have, I can say that this is sine of 40 over 4 should be equal to the sine of 60 over our unknown B. So all we got to do is solve for B and throw a bunch of stuff into a calculator, and we are good to go. What I think I need to do here is I don't like this b being in the denominator. That's a problem for me. I'm going to go ahead and multiply b up to the other side over here. Actually, I'm going to show you guys a slightly different algebraic step right here that's going to be ever so slightly less work. Basically, the deal here is that if you ever have a fraction being equal to another fraction, only if your equation is just one fraction equal to just another fraction, then it's acceptable for us to go ahead and flip these two fractions, right? So I'm going to go ahead and do that. And the reason is it's difficult for me to solve for variables that are on the bottom of a fraction. It's easy when they're on the top. And so I'm just going to rewrite this as 4 over sine 40 equals sine 60 over b. Excuse me. Now I'm just copying down the left-hand side over there. So let me actually do this correctly now. B over sine 60. Now it's more easy algebraically for me to go ahead and just multiply both sides by the sine of 60, and we will have solved for side length b. And there's our length b right there. So I'm going to be able to go to my calculator and get our approximate decimal for b. It certainly doesn't look like it's going to be anything that's going to pop out super clean, and that's okay right there. Now, before I do that real quick, I just want to point out, what do we still need to do here? Well, for us to know also, I guess I feel like I should have made my table of information for our solution here first. Maybe I can write this over here. Our side lengths A, B, and C, angles A, B, and C. We were initially given that angle A is 40, that B was 60, and that A was 4. Now, notice that one thing. I guess what I was saying here, before I even go to my calculator, it looks like we've got B now is basically the point. I've got B. What do we still need to do? Well, we're still missing one of our angles, but notice if you know two angles, then it's really easy to get the third. Our three angles are always going to add up to 180. These represent 100 degrees, and so there must be 80 degrees left over that goes in C right here. So I'll go ahead and throw that in my solved for purple. We just found B, and so our last thing to do is to get C. Now remember, in right triangles, if you knew 2 out of the 3 sides, you could use the Pythagorean theorem. Pythagorean theorem only applies to right triangles, so we've got to use the law of sines here. We can't use the Pythagorean theorem in this case. So we're going to have to do the law of sines a second time, and we'll go ahead and we'll get a value for C. So what do we got right here? Let's go to our calculator. And I've got myself a little Desmos window right here that I'm using as my calculator. And so what are we interested in throwing in here? We've got 4 sine 60. Oh, is it not? Can I seriously? Oh, wait, I can be in degree mode. I forgot about that. Okay, there we go. I'm so happy that I'm in degree mode now. Okay, and let me just check that I'm in degree mode right here with good old sine of 30. There we go, degree mode. I'm in degree mode now. Okay, I forgot that Desmos has that button right there. So I want 4 sine of 60 divided by sine of 40. And doing this, I'm getting a side length here of 5.389. So I'm going to go ahead and keep 3 decimals on that, I guess. 5.389. 5.389. All right, we've solved for our first side length right here. Now I think we can just go ahead and do that same operation, right? I just want to solve for C now, so I'm going to go ahead and do the same type of steps and solve for C. Similarly, solve for C. Now I'm going to remind us, can't use Pythagorean theorem only for right triangles. It will not relate the side lengths of non-right triangles. Interestingly, tomorrow, you're going to see that the formula that we're going to build tomorrow, the law of cosines, is in a sense, it's just like the Pythagorean theorem, just beefed up to handle non-right triangles is kind of what the law of cosines is going to be. So again, the thing that I'm noticing right here is that my best pair of information that doesn't have any rounded decimals or anything is the A's, right? I know A is a clean uh, angle and as a clean side length right there. Technically, I could use the B's to help me solve for C, but I hate having to use like, decimal values like that if I have the A grouping as my clean grouping here. So it looks like I'm going to use the two A values that I know and the angle of C to solve for the side length of C right here. So let me set up that law of sines statement here. Now, I guess what I'm going to go ahead and do is this. Since we talked about the flip step right here, just saying if you have two fractions that are equal to each other, you can just flip them, then you should notice that the law of sines is just as good upside down as it is right side up, which is excellent for you because that means that it's really easy to remember this. All you have to remember is that the A's go with the A's, the B's go with the B's, and the C's go with the C's. And other than that, it's kind of hard to mess this formula up. So I think I'm going to write this in a way that I know I'm going to want to see it, where there's the variable of interest is in the numerator. That's always what's easiest for me. So I think that I'm going to go ahead and set up here A over sine of A equals C over sine of C. And that's going to lead me to, what are we going to get here? 4 over sine 40 equals C over the sine of 80, which we had solved for. And all I got to do is multiply sine of 80 up to the other side, and we are done. So let me move this down just a little bit here. C is equal to 4 sine 80 over sine 40. And therefore C is approximately equal to, and once we've got it, we're done with this problem here. And so I'm going to bring back our Desmos here, and all I want to do is change this now to, what do we got? 4 sine 80 over sine 40. And notice how easy this is to change. Boom. Now I've got my C value right there. 4 sine 80 over sine 40, right. So 6.128 is, it looks like, what we can round that to 3 decimal places, 6.128. I'm going to come back here, 6.128. It looks like we've got our fully solved right triangle, or sorry, our fully solved non-right triangle right here. All right. So remember, angles are always easy. If you know two of them, then the third one is basically free. It's just everything needs to add up to 180. To get these side links over here, we got to do a little bit more work. But basically what you're seeing here with our law of sines algebra right here, it's never going to get any more complicated than this. We've seen that one of our strategies that's associated with this, since we're always going to be solving an equation involving two fractions, is it's always easiest to solve for a variable in a fraction if it's in the numerator. And because we're in a situation where we are a fraction equal to a fraction, it is always legal to algebraically just flip those fractions. Anytime else in your life, you can't algebraically do that unless it's just a fraction equal to a fraction, but that's always what the law of sines is going to be. And so in this setting, that's fine right here. So always set yourself up with a law of sines statement that has the unknown variable up in the numerator for you to do the least number of algebra steps that you can do. And we've solved our first non-right triangle this semester. Here we go. So let's go ahead and look at an angle side angle example right here, and then we'll move on to our slightly more bummer of a case right here. So angle side angle situation right here, and again, you're not going to know that it's angle side angle until you've drawn the picture and taken a look at it. I don't think these are taking that much room right there, but that's okay. Actually, well, that's okay. I'll bring it back. So again, let's set ourselves up right here. I know that I'm going to go ahead and draw my general triangle. So we always say that this is our A over here. I just draw the same triangle every time. Looks like B is really 15 degrees. This is our unknown C. And it looks like in this case, the one thing that's a little bit different here is that our C value is going to be 5. It looks like our A and our B are unknown. So I'm going to go ahead and set up our solution table over here, A, B, C. And A and B and C. So remember that when we're going to use the law of sines, one of the important things is that we have one completed partner pair of information. I need to know like A and A, B and B, or C and C. I have to have one of them like completed to use on one of my sides of the equal sign so that everything's known over there on that side. And do we have that here? Well, I'm seeing that we were given 35 degrees, we were given 15 degrees, and that we were given C is of length 5. So the first thing that you should be noticing here is we directly cannot use the law of sines yet. I don't have one completed partner pair of information to go ahead and begin solving here. But what is the one thing that we can solve for? Remember that we can always solve for the third angle if we ever know two of the angles. And so right away, right here, we have to solve for angle C first. All right, so it looks like 35 plus 15 is 50, and 180 minus 50 is going to give me 130. So it looks like that's my value for angle capital C. And so now with this value available for C, we can go ahead and we can use our law of sines to solve for both A and for B. So let's go ahead and set these statements up here. So it looks like C is my partner pair that's going to like do the work for me here. So I'm going to use C and C as my partners for one statement, and then B with a missing B, and then A with a missing A as my other side in the two cases that I'll do. And I'm even going to state them all together right here. Furthermore, it looks like the side lengths are the things we don't know, so I'm going to put that information on top. So I'm going to say that A over sine 35 is equal to 5 over sine of 130. That's one statement. That's my A over an A, and that's my C and my C. My other statement I'd like to make is the ones involving the B's. B over sine 15 should be equal to, same thing, the C pair, the completed pair. Go ahead and do this. In both cases, I'm just going to be multiplying the denominator underneath the unknown to the other side. I'm going to get A equals 5 sine 35 over sine of 130. And I'm going to be getting B equals 5 sine of 15 over sine of 130. And I can go to Desmos and easily get my decimal approximations for both of these guys. So let's go ahead and do it. No, I mean, the math for these is like identical here, right? Which is very convenient. So let me drag this back on screen here. We are looking for, we've got a 5 sine 35 divided by a sine of 130. This will give us our first piece of information. And I'm getting a value of 3.744 if I'm rounding this thing to 3 decimal places. And this was our A piece of information, so 3.744. Very similarly, we can go ahead and grab our other piece of information, and notice I literally just need to change 35 to 15, and I've got my calculation for B. And I'm getting 1.689. And there we go. Now, one thing I feel like is worth pointing out real quick here is that it's clearly the case that the triangle that I drew is nothing even remotely close to what the triangle actually looks like right here, right? I mean, I've got an angle of C being 130, but in my diagram it looks like it's about 45 degrees right there. So I guess the question is, what does this triangle actually look like right here? And what I'm thinking to myself is I should have angles of a very narrow angle of 15, a slightly less narrow angle of 35, and then a really huge angle of 130 here. So let's go ahead and see if we can draw something that looks a little bit closer here. I'm thinking that what this guy is looking like here is a little bit more something like this guy right here, where we've got 15 degrees here, 35 degrees here, 130 degrees here. And opposite the 135 is a 5. Notice that this is the longest side. Our second longest side for sure is the 3.744. And our 1.689 is clearly the shortest side right there. So this diagram feels a little bit more correct to me. But then again, like I said, I feel like there's value in consistency, even when it's not generally representative of the thing that you're doing. Drawing the same triangle with the same orderings, with the same labels all the time is just something that's going to prevent you from making stupid computation errors that aren't necessarily representative of you not understanding. It's just, if you do things different every time, then you're going to make small mistakes for bad reasons. And so I try to be really, really consistent with the things that I set up there. So let's go ahead and let's look at our first of our no good sides right here. Side length pieces of information. ASS, knowing angle, side here. Why am I? Here we go. So let's go ahead and look at our three cases. So again, this is my warning to you. This is the scenario in which if you identify that the information that you know is in the order of angle, then side, then you need to stop and have a little bit more awareness than we've had in the last couple problems and say, ooh, I better be a little bit careful with these. I remember Tony yelled at me something about this, so I better be careful. So here we go. Let's go ahead and just take a look at these guys and end up seeing what we see here. Now, you should importantly note that in our previous two examples, we were only given one side length. And so one of the interesting things here is we know two side lengths, but that means that we're missing two angles. So we can't just solve for a third angle with adding up to 180. It looks like we're going to have to solve for an angle using this law of sines rather than solve for a side like we've done in the last couple examples here. So let's go ahead and draw our very generic triangle here. Right? This is always where I put my A in this lower corner down here. I don't know it. It's always where I put my B up top. I don't know it. This is where I put my C. It's going to be our 50 degrees. A is 2. C is 1. And B is unknown right there. So maybe I'll build my solution table here. And so we're claiming that we know C is 50, A is 2, C is 1. So the good news for me is this. It looks like I know a completed pair, the C's, and therefore it looks like I should be solving for the capital letter of A right here, because in this case right here, it seems like I know one of the two missing pieces of information. Then if we can solve for A, we'll know 2 out of 3 angles, meaning we can solve for the third because they add up to 180. And once I know capital B, we can then use the law of sines again to solve for lowercase b. So let's go ahead and see if we can do that here. So I'm going to go ahead and set up my information where I know that the law of sines requires me to have one completed pair and then one sort of like half pair, and I've got that. It looks like the thing I don't know that I'm trying to solve for right now is capital A, the angle. So I want to have the sine of A being in a numerator, which is the not flipped version. We've been doing sort of the flipped version of the law of sines for the last two examples. I'm going to leave it in our original format here. So let's go ahead and do sine of A divided by A, which is 2, equals the sine of C over C. Okay, that worked out really nicely here. It looks like all I've got to do is multiply 2 over to the other side. And I mean, I don't even care about that dividing by 1, right? Dividing by 1 doesn't actually do anything right there. And so it looks like what we're going to want to do is we're going to want to take an inverse sine right here. So I think that I want to go maybe get a decimal for this, and then we'll apply the inverse sine operation to whatever decimal I get from this guy, and that will go ahead and give me my angle for A. So I need to pop over to Desmos here, and I need to say, hey Desmos, what's 2 sine 50 as a decimal? And so over here in Desmos, I'm going to say 2 sine 50. Now's where I'm going to stare at you and give you the crazy eyes here. What's going on here? And if you don't know, you should pause the video and stop and figure out for a second why I'm giving you the crazy eye right now. Okay, you're back. What types of values do we ever get out from functions like sine and cosine, and specifically sine and cosine? What's the largest and what's the smallest value you've ever gotten out from the sine or cosine function? And the answer is 1 and -1, because we're measuring the height and the width on the unit circle. Therefore, there's never been a time ever that you've gotten out a value as large as 1.5 from a purely just a sine function. If it was like 10 sine of x, then sure, it's going to go from negative 10 to 10. But the sine function itself only ever outputs values between 1 and negative 1. So the question is, what angle A is going to make this true? And the answer is, there is no such angle A that will ever cause sine of A to be 1.532. And therefore, there is no such triangle that has these measurements right here, is basically what we're concluding. And by the way, since I'm looking at Desmos right here, let's just do this. So I'm going to do sine inverse of 1.5. Oh, I don't even have to keep typing. Undefined. It's an undefined value. There is no angle that causes us to get out 1.532 from the sine function. Therefore, 1.532 could never be an input into the inverse sine function right there. So let's go ahead and kind of state what we just saw here. So, well, we can conclude, because we've arrived at an impossible scenario where there is no angle A that will make this information true, we can conclude that there is no such triangle that has these pieces of information right here. And what that's really going to mean to me is that it appears that we're trying to construct a triangle where maybe it's like there's like a length right here where the two sides like aren't long enough to like reach the other side over there or something like that. And here's like the angle A that we're trying to solve for. This is like one of those, you think of a triangle as being like where two lines have like come together and then there's a connection between them down here. But if the board that's holding them together is wider than the two of them added together, then they might not even ever touch, right? And if they touch here, then sure, we've got an obtuse triangle, acute triangle. But if the two side lengths are too short, then we're never going to make it. And I think that's one of our cases that we're arriving at right there. So no such triangle. If you can't do the math, then that means that there isn't an angle or a side length that satisfies that. And you'll always see this with angles, not with side lengths here. So, but yeah, that sine inverse thing seems to be a little bit weird for us now, right? So that's one weird thing that can happen in the ASS case. And this is okay. This isn't like extra work for you. This is just, you need, this is a weird thing if you just like come upon this and you're like, oh wait, is that an answer I'm supposed to maybe get? And the answer is yes. In the ASS case, it may be the case that the information that you've given results in there not being a triangle associated with the information you've given. That's a possible answer for the ASS case. Unfortunately, that's not the only weird thing that can happen in the ASS case. That's why it's a real ASS, right? So let's go ahead and look at another example here of some other things that might happen. So I'm going to go ahead and just carry on as though nothing weird is going on here, even though I'm anticipating something screwy happening. As usual, here's my A, here's my B, unknown, here's my C, unknown. Opposite of A is 3, opposite of angle B is 2, and I don't know C. So I'm going to set up my solving table right here, my solution table. And what do we know and what don't we know? We know that A is 3, we know that B is 2, we know that A is 40. So right away, I'm feeling good about this because I've got my partner pair that I know. I've got one piece of another partner pair. So we're going to use the law of sines to first solve for the angle B. Once we know B along with A, we can add those up to get to 180 with angle C. Then, since one of the two C's is known, I can use the law of sines to solve for the other missing part C, and we'll be good to go. Allegedly. I said a bunch of that stuff for the last one and it didn't work out. Let's see if it works out here. So I'm thinking to myself, I want to make the statement that involves the a's, and I want to make a statement that involves the b's. Since what I don't know is the angle, capital B, I want sine of b to be in my numerator so it's easy to solve for. So sine of b divided by b, which is 2, should be equal to the sine of a over side length a. The b's together and the a's together right there. This seems fine. I'm going to go ahead and multiply both sides by 2. And again, we're in the same situation we were before, where it seemed fine, but then we went to the calculator and we realized that something went awry, right? So remember that what we learned in the last one is that we had better be getting out a number between -1 and 1, or this just doesn't make sense as a computation for us to proceed with. So let's go to Desmos and ask what we're going to get for a decimal for this guy. And if it's not between -1 and 1, then we're done, and that the triangle just doesn't exist. So I want to come over here and drag my Desmos back on top here. And I am now looking for 2 sine 40 divided by 3. And hey, this looks like a number we can deal with, right? I'm getting a number that does, in fact, make sense. We can take the inverse sine of this number right here. So I think that I'm getting a sine of b, and all right, is approximately equal to 0.42, and we'll round this, 0.429. All right, getting that rounding right there. That 5 rounded the 8 up to a 9. And so now I want to ask you the question, what angle will output a sine value of 0.429? And here is where we need to be really careful about using our inverse trig functions. What I can do right now is I can go to Desmos and I can say, what is the sine, oh goodness, the sine inverse of 0.429. And what Desmos is going to tell me is 25.4 degrees. There's nothing wrong with that, but you guys should have learned a lesson back there in 7.7 and in 7.8 when we were solving equations. And that's to realize that every time that we're given a sine and cosine value, except for in some very special cases, there's really always like 2 results. Right? There's always going to be 2 different angles that are going to give you a height of 0.429, right? And what I'm thinking to myself is that there should be these 2 symmetric angles that both have heights that are the same, but are opened up to different angles. This one over here looks to me to be like the 25 degrees. So this one over here should be something like 180 minus 25 degrees, both of which you should notice that the height of my fingertips is equal, even though the width of my fingertips is not. When we do the inverse cosine function, we always end up with the partner pairs that look like this, where the, oh my gosh, I can't even do it, where the, I can just do it with my hand right here, where the widths of my fingertips are the same, but the heights are different. And again, they're symmetric over that line that's the x-axis. Here we're symmetric over the line that's the y-axis, right? So I really know that there's actually 2 possible answers. Very important. Could be 2 answers. So what I'm going to do is I'm going to draw a line of height 0.429. And it seems like it could be either of these angles. Now remember, since the inverse sine function always outputs values on the right half of the unit circle, right? I drew this picture a whole bunch of times last chapter. I believe I used the color orange quite a bit for this one. Right? This is where sine inverse lives. Right? Always lives on the right-hand side. So what I'm seeing here is that from Desmos, we're going to get that B should be the sine inverse of 0.429, and that Desmos is telling us that this is going to be 25.4 25.404 degrees. That's this guy right here. It looks like that's about my 25.404 degrees. So my question to you is, what's the other one over here? Well, to get to this other one, what we should recognize is that this angle is the same as this angle right here. So this, to get from our starting position up to 25, we started at 0 and we added 25 degrees. I would instead like to start at 180, and I'm going to subtract off 25 degrees to get there. So let's go ask Desmos, what are we actually getting for this guy right here for our other possible solution? And I can just do 180 minus. And it's going to tell me our other possibility is the 154.596. So it looks like there's two possible angles. And you know, that 154 seems huge, but we've already solved a triangle that worked out just fine with a 130-degree angle in it. So, I mean, you should be picturing something like this. I think that's not wildly unbelievable. There could be a 154 angle. I mean, that's just making a triangle that's got like a really, really wide top right here and a really long flat base and two really small angles on the sides right there. I don't think it's the most unbelievable thing that I've ever seen. But what? But what? And look at the top of your screen right now. Now it's gone. Look at the top of your screen right now. What's the other angle that we have to work with in the triangle? This triangle is guaranteed to have a 40-degree angle in it. So it seems like this 154 that we got is realistically an angle that could potentially have been in this triangle. But given that another angle in the triangle has to be 40, 40 plus 154 is 194. Those two angles alone, that makes too much because 180 is what everything needs to add up to. So what I'm saying to you is this. There really were two good candidates right here, and we found both of the good candidates. But it turns out that this one is not going to be associated with any triangle because the angle would be too big. So let me kind of state a bunch of this stuff right here, and let's get Desmos out of the way for a second. So we found that it may be possible that two different triangles might agree with the initial given information. One with B equals 25.404 degrees. One with B equals 154.596 degrees. However, given that A is 40 degrees, and by the way, I'm going to call these B1 and B2 just as our options for B's. B2 equals 154.596 degrees is too big. 40 plus 154 equals 194, which is greater than 180. So that won't work. Let's carry on with just B1. Okay, so the thing that happened here, that was the excitement for a moment, is we actually found there was two possible, there was maybe like two candidates of triangles that could have worked out, but if we used one of the values that we're getting out for B, it would have been too much when joined up with A to still form a triangle. So we're going to go ahead and kind of ignore. So we want to recognize that that might have worked. In this case, it didn't work right here, but it could have been that there were two different triangles that are possible to be created with this information that was given originally right here. So I think that what we can do is we can conclude that our B value here must be 25.404. So Now we can continue on with solving. So the next step that I see here is as soon as I know two out of my three angles, I'm immediately going to find the third angle right there. So I'm going to go do 180 minus, oh wait, let me bring it, I'm sorry, I'm doing Desmos stuff here without showing you. There's some Desmos stuff. I'm doing 180 minus the 40 that I know, oh my gosh, minus the 40 that I know, minus the 25.404 that I know, and I'm getting 114.596 must be the angle C that we're looking at here. 114.596. And now all I've got to do left is one last little law of sines to solve for our C stuff right here, and I think that we'll be done. So I always like to use my cleanest values possible, so I'm still going to stick with using the A stuff right here, and I'll do A stuff with C stuff here for the law of sines. So let's proceed on with B1, and then we'll look at our final problem of the day. So let me switch back to black here. We're going to do these. Oh, wait, sorry. Hold on. What are we solving for? We're solving for a side C. So I just started to write sine as a numerator. I want to have my side lengths on top right here. So I think I'm going to do A over sine A equals C over sine C. All right, now I got to remember what all these were. A and sine A are 40 and 30, or 40 and 3. That's 3 and 40. 3 over sine 40 equals C, the unknown, over the sine of, and this is that angle that we just solved for that's up at the top of the screen right now, 114.596. All right, so all I've got to do is multiply this to the other side, go to the calculator, and we are done with this guy here. All right, and let's see here. What do we got? 114.596. So we got 3 sine 6 divided by sine 40. And I'm getting 4.244 if I'm rounding that thing correctly there. 4.244. And now we've got our side length C, and therefore we are done. All right. So let's kind of review what we've seen, and then we'll go hit our very last example here. So what we've seen now is we've seen that in this undesirable ASS case right here, is in our first ASS case, we found an impossible triangle, one that there was no solution at all. In the second example that we saw there might have been two solutions, but one of them didn't work out. So my question to you is, what do you think we're going to end up seeing in our final example right here? Hopefully you're a reasonable guesser, and you can deduce what you think is going to end up happening for this guy right here. So let's go ahead and do our final example of the day, our last look at some ASS here. So again, consistency is the hallmark of a champion. Keep on doing this stuff the same way. Keep on labeling this triangle the same way. A is 35. B is unknown. Angle C is unknown. Opposite of angle A is side length A, which is 6. Opposite of angle B is side length B, which is 8. And lowercase c, also unknown. I'm going to set up my solution table here. Side lengths, angles. I've got angle A is 35 degrees. Angle B we don't know. Angle C we don't know. Side length A is 6. Side length B is 8. Side length C is unknown. So again, setting up my solution table really helps me see what I'm doing strategy-wise. A is the completed pair, so that's one grouping I'm going to use. B is the pair that I know half of, so that's the other grouping I'm going to use. Once we've used the law of sines to solve for angle B, we'll know 2 out of the 3 angles, and we can solve for angle C. Once we know angle C, then side length C is all that's missing, and then we can do a law of sines to solve for that missing side length. So let's go ahead and do the dang thing here. So I'm going to set up my A's and my B's and B's. I see that angle B is the thing that's unknown, so I want to put my sine of B needs to be a numerator up here. So I'm thinking I want something like sine of 35, that's my A, divided by side length A, that's 6, should be equal to the sine of the unknown angle B divided by my side length B, which is 8. I'm going to go ahead and multiply 8 to the other side, and just flipping this thing around right here just because I like having the thing I'm solving for being on the left for some reason. And let's go to the calculator and see. Remember that it's possible that we're going to get out a number bigger than 1 or less than -1, and we can't even do this problem anymore. So it is kind of worthwhile to like stop and do the math at some of these steps right here, since we know that in the ASS case, some funky things can happen. So 8 sine 35 divided by 6. And okay, we're getting a reasonable number here. It's between -1 and 1, which means we're at least still cruising along. So I am going to be, okay, here we go. So I'm going to be getting that sine of B should be equal to 0.765. So again, what we know is that there are now two possible angles. Right? We know that when we draw our unit circle over here, that we're asking what angle has a height of 0.765 on the unit circle. So 0.765, a little bit higher up there. Here's our height of height equals 0.765. And it clearly looks like there's an angle there and an angle there that might work. I know that when I go to my calculator and I say, what's the inverse sine of this thing? I know it's going to give me this angle on the right, because that's always the one that's associated with the side of the circle that inverse sine outputs values on. But I know that I'm going to need to go hunt for the second one and consider the possibility that it's valid as well. So let's go to Desmos and ask, what is the sine inverse of B? Or sorry, apply the sine inverse to both sides of this equation right here and ask what's the sine inverse of 0.765. That will give us the B that's going to be here. I'm also going to want to know what's this one over here, and I can always get that by doing 180 minus. Instead of starting at 0 and adding that much angle, we're going to start at 180 and subtract that same amount of angle. That's right there. All right, so I'll mark this to indicate those are equal angles right there. So let's go ask Desmos what we're going to get. And we're going to do our sine inverse 0.765. And it's telling me 49.907. Or B equals 180 minus 49.907. So I'm going to call that B1 and B2. So I'm going to say, like before, we found two candidates for B. And 180 minus this number is 130.093. And now we ask the question, are they both possible, given the other angle? What was our other angle that we were given? Well, we were given that angle A is 35 degrees. here's what I want to do now. Is I want to identify that both of these are legit. Right? Because 35 degrees added on to 130 is only 165. That still leaves us 15 degrees left over to get the third angle. Certainly 35 and 49 work out to leave enough angle left over for a third one right there. So it seems like in this case, both of these b's are going to be just fine for the triangle that we're trying to solve. So what I apparently need to do now is go recognize that my solution table is now insufficient because it's built to just talk about one triangle. I need to talk about the fact that there's actually two potential triangles here. So I'm going to set up, I'm going to redraw my solution tables to indicate that there's actually two sets of solutions here. So an A, a B, and a C, an A, and a B1, and a C. And I'm going to add some subscripts as necessary. And it doesn't matter which one you call one and which one you call two. I just want to acknowledge that there's two solutions. So I've named them, one being the smaller and two being the larger. So that's just it doesn't matter though, as long as you kind of keep them organized right here. All my ones will end up over here on the left. All of my twos will end up over here on the right. So let's do the same thing here. A, B, C, A, B, C. Now, let's remember what we were given. We were given angle A is 35, A is 6, and B is 8. We got 6, 8, 35. That stays. 6, 8, 35. 6, 8, 35. We just found two different B's, so I'll leave that as B2. So it seems like the first choice that we have for B is the 49.907, so I'll put that here. The second choice that we have for B is the 130.093. I'll throw that there. So it looks like in both cases, we can solve for C just by adding up to 180. And in both cases, we have one law of sines left to do to solve for C with the two different angles associated with angle C. So let's go ahead and go back to Desmos and do our subtractions from 180 to see where we're at here. So it seems like I want to do 180 minus 35 minus 49.907. That's going to tell me my first other angle is the 95.093. And by the way, it looks like this C is going to be different than the other one, so that had better get a subscript of the 1. And it looks like side length C will then also be different. Here, that's going to be different, and that's going to be different. So these are the ones that are different from each other. I want to label which grouping they're with. The lowercase a, lowercase b, capital A are consistent, so I don't need to identify what group they belong to right there. Very, very, very similarly, we want to go check out this other subtraction over here, and we want to subtract this guy off of subtract off 130.093. And in this case right here, wait, did I? Oh yeah, okay. And it's giving me 14.907 as my other angle here. So 14.907. Oh wait, let me get the right color here. I got confused because I saw decimals I recognized, but it makes a bunch of sense that these decimals have to be opposites of each other because these numbers need to add up to a whole number of 180. So when you subtract one, you get the other and vice versa. So, so we're cruising on both of these right here. We're almost done. We just need to do the same law of sines for both of them. So I'm going to continue keeping these spread out here. So to solve the first triangle the rest of the way, we have one more law of sines. To solve the second triangle the rest of the way, we also have one more law of sines. So let's do the algebra for both, then we'll go to the calculator for both, and then we'll call it a day here. So, so these are our last ones. Again, I recognize that the A partnership is both complete and doesn't have decimals in it, so it's definitely my buddy here. I'm recognizing the thing I'm solving for is a side length, so I want side lengths up in the numerator. So I'm going to set up A over sine A equals C1 over sine of C1. And I'm going to do the exact same thing over here. A over sine A equals C2 over sine of C2. Over here, this is going to give me 6 over sine 35 equals the unknown C1 divided by the sine of the 95.093. Very, very similarly, 6 over sine 35 equals the unknown C2 over the sine of 14.907. In both cases, because we smartly put our unknown part on top, we just have to do a single multiplication and we're done. Multiply over this denominator term, the sign of the gross decimal to the other side, and we're going to the calculator. So I'm getting here C1 equals 6 sine 95.093 divided by sine of 35, and C2 equals 6 sine 14.907 over sine of 35. Let's go to the calculator and let's hit up a C1 and C2 and we will call it a day here. Oh, excuse me. We will summarize what we've seen because I need to shake my fist at you slightly more and then we'll call it a day right here. So back to our calculator for our last calculations. I want to compute 6 sine 95.093 divided by sine of 35. I'm getting 10.419. By the way, I guess the other thing I want to do also before we wrap this up is say, what does it even mean that we're getting two different triangles here? And so we should pause for a moment and kind of like convince ourselves that this actually makes sense, what just happened right here. Yeah, okay. Um, and I'm getting here a 2.69. Let me just make sure I'm not going crazy right here. Yeah, 2.69, 10.4. Okay, cool. 2.691. Just saw some decimals I didn't recognize on my notes and I thought I made a mistake, but I have not. I was just looking at the wrong problem. So 10.419 goes here. 2.691 goes here, and I think that we are all good with our two full complete solutions right here. So I'm going to put a big old box around this guy here. Two different triangles that we just found that both satisfy that initial chunk of information here. So the question is, well, what do you mean there's two different triangles that have those pieces of information here? So let's go ahead and draw a picture that represents exactly what we just saw right here. Get out of here, Desmos. So that you're convinced that it is in fact possible for this guy to happen right here. It looks like in this case right here, we had this triangle right here seems to have all these more modest angle measurements, at least right here. One angle slightly bigger than a 90-degree angle, but like all these are like, I don't know, no extreme angles. Here we're getting two angles that I would consider like extreme in a triangle, one very small, one very large. So approximately draw each of these guys right here and then see where the distinction comes in. I'm going to draw slightly smaller because I'm going to draw a collective triangle in the middle. So this guy right here, I'm seeing actually looks quite a bit like this, the general triangle that I've been drawing right here, where let me fix this ever so slightly so it actually looks like exactly what we've got. So this is going to be, so we're trying to draw this solution right here. And in this drawing right here, I can put my A equals 35 where we normally put it. That's our 35. This is going to be our B. This is going to be our C. And in this case right here, we found B to be the 49. Oh, wait, no, I do want these labeled slightly differently. That's okay. This is our C, and this is our B. We had found that B was the 49.9. I'll abbreviate our decimals a little bit here, and this is the 95.1. And I think that hopefully these all look like pretty reasonable. Like I like actually maybe drew this kind of correct right here. Opposite of the 49.9 was side length 8. Opposite of the 35 degrees is 6. And I hope that you will also believe that the way that I just drew this, this does look like that's an 8 if that's a 6. This is a smidge longer than that one. This is clearly the longest side right here, and it's associated with this longest side length of 10.42 right there, right? On the other hand, our other possible triangle that we got over here was one where the 35-degree angle is the same, and that side lengths of 8 and 6 are the same. There's my 6, there's my 8, there's my 35. That's my A. And then again over here, we're now going to see that our C is this 14.9 right there. And this right here is our very, very large angle of our 130 degrees right here. That's our B2. That's our 135. That's right there. So in general, there's sort of this collective triangle that's between the two right here that looks, it's outside, like the one that we drew on the left. But you can also sort of imagine us making this triangle right here, to where this is the 6 and the 6. This is the 8. This is our, oh yeah, I didn't label this side length down here of the 2.69. This whole thing is the 10.42, but just this piece of it right here, that's the 2.69. The 35 was common to both. And then our overall angle up top here, overall, this was a 95.1. But inside right here, this was our 14.9. So what you can imagine for yourself is that we were really taking this overall triangle and drawing, just like this was a side length of 6, we would draw another side length of exactly 6. And notice, if we had drawn this at a different angle, then this side length of 6 would have like stuck out past the bottom or would have not touched. So this is like the exact angle at which we could have gotten another side length of 6 in there, right? So I'm going to put an arrow there and an arrow there. That this is sort of like the collective diagram of everything that we just saw, the two different angles that have, and I guess the last thing I want to do is just highlight what are the consistent things between the two. We were given the 8, the 6, and the 35, right? So those are the things that remained the same between the two triangles. All these other things are the things that we had to solve for to find the ways in which they were slightly different from one another. So our conclusion for this is to say to you, when you see the ASS scenario, when you're given information and you immediately draw your triangle and you realize that you know an angle and then a side is your information in order. An angle and then a side and then a side. An angle and then a side, and then a side, where you know two sides, one angle, and the angle's not between the two sides, then you know that there's a bunch of funny business that might happen. You might end up with no possible triangle. You might end up with two candidates, but where one of them didn't work because it would be too many degrees for the 180 on the inside. You might end up in a case where there's two candidates and they both work, and you need to solve for both triangles, right? So the ASS case has several possibilities, 0, 1, or 2 solutions, and you need to make sure that you can identify which are the 3 possible cases right here, right? Now, the good news for you is that at the very, very beginning of today, we classified like all the cases of which we're worried about. We're never going to solve an AAA triangle. ASA and AAS are always going to work out with only one possibility. Nothing screwy going to happen right here. Side angle side, nothing screwy is going to happen here. Angle side angle, that's the 3 cases that we had to worry about today. Side side side, we're not going to get anything screwy happening here with our law cosines either. So really out of all these possible cases, it's the angle side side case. That's the one where you need to say to yourself, ooh, I better be careful. All the rest of these are going to be pretty directly solving, and you can kind of just use the formulas, do a little bit of algebraic solving, go to your calculator once, and you're going to be done. It's the ASS case out of all this stuff right here that's the one that we really got to watch out for. You just saw all 3 possible outcomes of the ASS case, 0 solutions, 2 candidates but only 1 solution, 2 candidates and actually 2 solutions. And we got to be able to handle all 3 cases right here. So this is sort of your tough problem for this week, is the ASS case for solving non-right triangles. Tomorrow the formula is a little bit harder, but we don't have any weird cases out there. It's gonna be a little bit more straightforward, just with a slightly more complicated formula, but no like difficult like, oh, do I need to consider these other things, and do I need to draw this diagram, and how does this even work out, and am I sure that I got the right solutions? And there's a little bit less of the ambiguity in the law of cosine stuff out there. So again, next video, a little bit harder formula, but no weirdness. Today, really easy formula, but there's a case that we just have to be more careful with than the other cases out here. And so exercise that caution with your ASS to make sure that things go smoothly for you there. So that wraps it up here today for us for the law of sines. In the next video, we're going to get law of cosines. It's going to feel very similar to today. It's just that the formula is going to change. I think the video should be a little bit shorter as well because we don't have so many special cases to go over with the law of cosines. I will see you guys for 8.3 with the law of cosines in the next video. Have a good one.